everyone. So this next section, 7.4, is going to take up the entire, hopefully 30 minutes of this video. So this is 7.4 in Steck. Right, oops. Let's see. And it's going to focus on one of the application of operational amplifier, which are op-amp filters, right? So as we learned before, right, just like transistors, we can add a low pass and a high pass to it. We can do the same thing with operational amplifier, of course. So this first one, so it's going to let current through. So this is actually going to be a high pass filter, right, where it'll amplify high frequency signal, but knock down a low frequency signal. Okay, so how can we determine this? So if we want to figure out the gain of a circuit, right, we're always concerned about V out over V in, right? And on a single feedback loop like this, that's basically whatever the impedance of the feedback part is divided by, oops, there's no negative sign in this one, divided by the impedance of the input side, because there's only one current, right? Using golden rule number 1. Okay, so what's the impedance of this feedback part? Well, there's just one component there, that's R, right? And the impedance of a capacitor, as you remember, right, is I over omega C. So we're going to have a fraction inside a fraction. Okay, and this is going to be negative I R. Well, I'm going to put the omega in front, omega RC. Okay, and just as before, right, 1 over RC is going to determine where the omega F3 dB is. Well, the omega 3 dB, right? That's kind of like the corner frequency, sometimes written as omega C. Okay, so as you can see, right, the gain of this circuit, right, is basically proportional to the frequency. Okay, and what happened is that, you know, at higher and higher frequency, right, you're going to get bigger gain. In fact, this is going to cause some issue, and I'm going to skip to that. So if you're try and follow it with the book also introduces the low pass filter, but I'm going to talk about the issues with the high pass filter first. Okay, so this is with the differentiator. What I would like to refer to it is actually the high pass filter, because that's essentially what it does. Okay, so the gain of the high pass filter, right, is I omega C. There's a negative sign somewhere. Oh yeah, I did. Yeah, that's a good point. Right, this is actually in the denominator, right? And the way that the book gets it is you multiply the top and the bottom by I, which is basically multiplying by 1, right? And then I square cancel out this negative sign. And that's I omega RC. Right, that's actually the gain. Okay, good catch. Okay, so one of the things with this is that, well, as the frequency increase, right, the gain increases like this. That's what it's supposed to do in theory, but in practice, what happens is that your input's going to have some noise in it due to environmental issues or just interference from other part of your circuit. Okay, and pushing very high gain through an op-amp basically will cause your amplifier to destabilize, meaning it doesn't have a good open loop gain anymore, because this beta function is going to start changing, because the harder you work this amplifier, right, the more the temperature will increase, and then this beta just change, either increase or decrease, and it's really hard to predict what's that going to do. The solution is actually to basically cap this high frequency gain, where, if you want a amplifier that does 10x, right, there's no reason for you to go to 1,000 times gain, at that very high frequency, because what's going to happen is you're just going to get some noise in your input or your output, and those noises going to be dominant as opposed to your real signal that you're only trying to amplify by a factor of 10. Okay, the way we do this is basically adding a little small capacitor on the feedback loop. Right, remember this is the feedback loop, and this is the input loop, right? And we add a little resistor to the input loop. Okay, so what does this do? Okay, on the input side, right, by adding this little resistor, right, as the frequency increases, right, remember that the impedance of a capacitor is I omega c over omega c, right? As this goes to a bigger and bigger number, the impedance on your capacitor gets smaller and smaller, right? This little r here basically makes sure that the input impedance, meaning the impedance of this current to go into this virtual ground, right, never actually goes to 0, because you don't want that, because then you're going to have some number r dividing by 0, which gives you infinite gain. Okay, on the feedback loop, why do we add this little capacitor there, right? That little capacitor basically allow high frequency noise either from the input or the output, right, to bypass the resistor. Get rid of this, right? Because as we said before, right, the impedance of the capacitor goes to 0 at high frequency. So this is basically a way to have a high pass filter that has some high pass cap to it that you cannot go over. Okay, and this is going to give you an interesting design where let's say we take the log of the gain, right? So kind of like on the decibel scale, if you multiply this by 20, this is basically the attenuation AdB, and you take the log of this angular frequency. What happened is that a regular differentiator basically has this linear function, right? The gain will just go to infinity, where this new one that we added this small resistor and capacitor to is known as the tempered active high pass amplifier. Okay, and what that does is that it tempers it, because it basically has this little roll off. In fact, the gain actually goes to 0 as the frequency goes to infinity. So the book doesn't do this, but you can actually predict this behavior theoretically, right, by adding these impedances to your calculation. So let me just show you how to do that. Okay, let's see, back. Okay, so right, so by adding the capacitor and resistor, the small resistor to your feedback loop and your input loop, okay, essentially what you do is you change what ZF and Zin is, right? So I'm going to copy down this equation that we used before already, right? ZF, right, if you go up here, right, it's basically a resistor parallel to a capacitor. Of course, that's going to move this around. Okay, so I'm going to call that capacitor CF, and then the resistor RF, just to make it a little easier for me to refer to them, because there's going to be 2 capacitors and 2 resistors. Okay, oops, it's not multiplied together, they are parallel to each other, right? So it's the impedance of this resistor F, right? Well, things that are parallel to each other, right, we do this 1 over thing, right? So this is going to be 1 over I omega C, which basically puts the omega on top and the I in the denominator. And the resistor is just a resistor. So that's pretty simple. All this to the -1 power, right? The common denominator between these guys are, I'm going to put an RF on top and an I on top there, right? So, and then once I have the common denominator, I can flip it upside down, right? I'm just multiplying by 1 on both terms. Okay, so it's I RF on top, and then omega RF CF on the denominator. Okay, Zn, right? That's even simpler. That's just a capacitor and resistor in series. So that's I omega C. And this is going to call that C1. And then this is going to be R1. Okay. Before I move on, I'm just going to do a common denominator between these two guys also, so that it's easy for me to do a bunch of fraction gymnastic in a little bit, right? So multiplying this by R1, multiplying this by R1, and then I need to multiply this by omega C1, so that means the numerator has to be multiplied by omega C1, right? Oh, and no, that's it. So that's what, oh, I don't need to do this. Right. Why would I do that? Right. The thing that's in the fraction is just omega C1. Okay. In fact, I'm going to clean this up a little bit. Sorry about that. Okay. Omega C1, omega C1, because I'm just multiplying by 1. Okay, so the numerator becomes I plus omega R1 C1. The denominator becomes omega C1. Okay, so the gain is, right, the ZF over Cn. So that's just I RF over omega RF CF over I plus omega R1 C1 over omega C1. Okay, so this is in the denominator. That means this just goes in the numerator. I'm going to put the omega in front. RF C1, and these two just get multiplied to each other. Ooh, did I write something wrong? Yeah, there's something wrong here, right? That's the denominator. I forgot the I in the numerator here, of course. This one here. Okay, so this is actually plus I. So this gets multiplied together, and it just turns into this I plus omega RFCF, and then I plus omega R1C1. Okay, that's your gain function. Okay, so, okay, this has some interesting properties still, right? So as omega goes to 0, right? This still goes to 0 because, you know, you have a denominator, the gain goes to 0 still. But as omega goes to infinity, instead of going to infinity, right, the infinity means this term dominates, okay, and this term dominates, right? So since you have a product of omega, the denominator is basically proportional to omega squared. The numerator is proportional to just omega. The gain actually goes to 0 as the frequency goes to infinity. Okay, so that's just what this roll off does. Okay, in fact, you can probably predict this by just drawing this triangle here. So this is kind of nice, and you kind of have this flat part here that you still want to stay away from because, you know, you don't have an exact equation for that. But what that does is that, well, if you want your differentiate your high pass filter to work well, you know, have some gain and, you know, these frequency, then you just kind of stay away from this temper part. It's just to get rid of high frequency noise that you're not expecting in your signal. Okay, so that's what this tempering does. All right, so that's how we can get a high pass filter on our op amp. Next, we're going to do a low pass filter because that's what we always do. We do a high pass, we do a low pass, right? So this is known as an integrator, but we would also know it as a low pass filter, meaning it amplifies low frequency but knocks down the high frequency. Okay, right? We just reverse the placement of the capacitor and the resistor. Okay, I'm going to show you guys how to do this once again, right? You have CF over Cn, right? That's basically what the gain of all these single current feedback loop operation amplifier does. Okay. ZF in this case, right, is the capacitor, I omega C. Zin is, of course, R. Okay. So taking this ratio, right, the gain is going to be well, there's a negative sign in front. Okay. Omega RC. Okay. Now in this case, right, of course, the omega is in the denominator, so as we expect, right, as omega goes to 0, the gain actually goes to infinity, which is going to cause a problem. We're going to see how we get that. Okay. But as omega goes to infinity, the gain goes to 0, as we expect for a low pass filter. Okay. So we're going to see some issues with this, right? This infinity gain is going to be a problem because even the open loop gain of our op amp is only like 25,000. We're not going to get anywhere close to infinity, if you can, right? The way you fix this is basically add a resistor, a large resistor that's in parallel to this capacitor. Okay, because what happened is that if you have some even tiny bit of DC offset, that's going to give you a constant, right? If you have a tiny bit of DC offset, let's say your VN is not centered exactly at 0, around 0, it's just like a millivolt off. Okay, that's going to get amplified a lot by your low pass filter, because basically technically the application at DC is actually infinity. You never really get to 0, but you don't want that large gain to be dominating what your output is going to be. You actually want the signal. Okay. So what this does is that it gets rid of this DC offset. So how does it do that? Okay. So we get this tempered version of it, where this is the integrator. Okay. Okay. The integrator, basically, the gain is linear, right, with frequency. So it goes to 0 and it goes to infinity as the frequency goes to 0. Okay. This temporal one, by just adding that large capacitor there, that's going to give you some cap. Basically, there's some maximum gain that your circuit can have, no more than that. Okay. We can do the same derivation again. This one's even shorter. So remember, once again, we keep using this equation over and over again, right? Gain is the feedback over the input impedances, right? The feedback loop, right, in this case is similar to what we had before, right? We can even copy it, right? Because it's basically the same thing, right? So so is this here, okay? So I'll show you with that correction of the IRF, and then the product plus I. Okay, let's go back down. IRF, and then omega RF CF plus an I. Okay. Okay. Zn, in this case, is just going to be Rn. Okay. Did the book call it Rn? Let's just call it R. Okay. I'm going to call it R1 just so that make sure that we have a subscript for it. Okay. Okay. So the gain here, right, is going to be IRF over omega RF CF plus an I divided by R1. Right, this is in the numerator denominator, so actually goes back to 1. Goes to the denominator. So just combine these fractions together. R1 times all this stuff. Okay. So let's see how this behaves. Okay. So as omega goes to 0, which is the point we're interested in, right? Right. As this term goes to 0, the gain actually goes to negative RF over R1, right? And that's exactly what this sets this line here. Okay, that's your maximum gain that you're going to get from your low pass filter. Okay, hopefully at omega goes to infinity, we still get a gain that goes to 0. So there's the only thing that's omega here is in the denominator. So of course this gain will go to 0. Okay, and that's exactly what we want for our tempered low pass amplifier. Okay, so that's sort of the two circuits we're going to be playing around with in the lab with. But I'm going to point out a couple of more things that the book goes through, which is really nice for the book to do that. Because when you start building the circuit, you're going to say, oh, well, there's something wrong, there's some noise, and can't figure out why. And typically, these are the typical causes of this problem on your amplifier. Okay, the first one is known as input bias current. So the input bias current, okay? Remember the first golden rule of op amps, right? I tell you that, oh, the input draws no current. Well, that's kind of a lie, because in order for you to measure the voltage at the input, you have to draw a little bit of current, right? Because there's no way for you to measure things without touching it, right? So in order to measure this voltage, right, the transistor, or overall the op amp, actually draws a little bit of current. Okay, so in the real world, what you will do is actually look up the data sheet, okay, and look up what this parameter is. Okay, I'm going to do this for the LF411, which is the ones we're going to use in the lab. I'm going to have you guys look up other ones that may be better or worse, and then we can see, compare and contrast them. Okay, if you do a little search on the internet for LF411 data sheet, pretty easy to find. Typically you'll find data sheets from different companies. Texas Instrument, is one of the bigger integrated circuit manufacturers, so I would trust the data sheet from them more than a data sheet from random company .org or actually .biz or something like that. I don't know what the internet address would be, but like big company that you may have heard of, like these are this company that makes your calculator, is because they put all these chips in your calculator and they can actually allow you to do that. Okay, if you look this up, you'll get a PDF, and on the first page PDF basically kind of gives you the advertisement. So if I was looking for a chip, I would look on this first page first to see what the specifications are for this particular op amp. And let's just go through it kind of quickly. But the thing we're going to be focused on at first is this, right? I'm going to use a highlighter. I'm not going to highlight the rest of it. Okay, it's this input bias current. Okay, we're going to describe how that affects your amplifier. Okay, but also you have a low input noise current. Noise meaning just if you have nothing there, there'll still be some wiggle noise. So this is going to be 2 femtoamp. The F means femto, 10 to the minus 15, divided by the square root of the frequency that you want to use this at. Okay, there's some supply current. So when the thing is not amplifying, this still draws a little bit of current to keep things on. Has a very high input impedance, 10 to the 12. I think I said giga, so this is actually whatever is after. Giga is 9, so tera is a tera ohm. Okay, 1 tera ohm. Okay, it's actually bigger than I stated in the previous lecture. Okay, there's low total harmonic oscillation. It's just that there's some constructive and destructive interference inside your op amp. They try to not have that. So what it's used for is an integrator, right? It's a fast digital to analog converter. So we'll talk about that. You can use it also as a sample and hold. We actually have that, going to have that circuit also. But so what we learned so far is that we use this as an integrator, right? Okay. There's some description of it. There's different packages. The ones we're going to use in the lab are DIP. DIP stands for double inline pins, and I'm going to show you a picture of it in a second. Okay, there are other packages. This small outline, which is going to be a surface mounting that we're not going to permanently mount stuff to anything. Okay. But if you keep scrolling down, right, so it seems like, oh, we already found this number, right? That's the typical number. Typically, what you usually design things for is kind of like the maximum tolerance instead, okay? If you keep scrolling down, you're going to get to a page called specification. These are going to be the maximum minimum rating for this particular chip, okay? So the maximum voltage you can actually put at the voltage supply, so this is VCC and VEE, is actually 18 volts. If you put technically 18.1 volt on it, maybe, right? Even 18 volt, if there's a little fluctuation in your DC power supply, you're going to start breaking the circuit inside. Okay, so don't put anything above 18 volt. In the lab, we're just going to run it at 15. That's what we're using it for. Okay. And you want the input voltage to be less than 15 also, because you may have cases where the gain is less than 1, but your input still has to be less than 15 volts. Okay. There's more recommended. So instead of the maximum, they recommend you use it with this. You want to at least bias it by half VCC to be 3.5, so you can't, work it at like 2 volts or something like that. But what we're going to see is that we're going to get to the third part of this, which is electrical characteristics. And all of these are tested at room temperature, okay, and running at VCC of plus or minus 15. So that's how they test it in their lab. Okay, and we're going to see that the input bias current is going to be here. And there's going to be 2 lines there for some reason. Okay, one is going to be at room temperature. The other one's going to be at a higher temperature. Okay, notice that when the temperature increases, right? So let's just compare the maximum number, right? At room temperature, you're going to get 200 picoamp. Pico means, right, 10 to the minus 12, right? But if you increase the temperature to 85 degrees Celsius, you're going to increase that input bias current to 4 nanoamp. Okay, so which is going to be 5 times 4, which is 20 times bigger. Okay, so typically you want to run these op amps at around room temperature. Okay, so what is the typical versus maximum, right? Typical meaning that when they make the thing and they measure 100 device, the average is going to be about 50 picoamp. Okay, the maximum means that, oh, if one of these device, is at 201 picoamp of input bias current, they chuck it. Yeah, they cannot sell that. So that's the maximum. Okay, and typically when you're designing things that you want to work for a long time, you design it so that you deal with the maximum number as opposed to the typical, because you don't want, because the typical will actually, will have some fluctuation in it. Okay. Okay. So remember that the feedback current, right, that we're using, let's say, which is, the current that's going through the feedback loop. Let me see like this, right? This is the current, right? That's going to be typically around like maybe a milliamp. Okay. So for example, if your V out is 10 volt, then your RF is, whatever that impedance is about 10 kilo ohms, right? You're going to have about 1 milliamp. So this picoamp, right, is going to be about 8 orders of magnitude less than that. Okay, so typically it's something that we don't have to worry about, especially in our lab where like our resistor is plus or minus 10%, right? But there are cases where this can cause a problem. Okay, before we tell you what the cause, what that problem could be, so there is a way to fix this. The way you fix this is basically by putting in a variable voltage supply at your input, because what's happening is that there's a little bit of current leaking into here, right? Because you have to keep sampling the voltages. Okay, what you do is you connect this potentiometer also known as a variable resistor, right? That's what the symbol is. So when you dial this resistor up and down, you get a different resistance, okay? What that does is that it'll supply that current, okay? And so instead of drawing current from your VN, it's just drawing, the input is going to draw the current from this large resistor, okay? And that way you're kind of supplying, or you're offsetting this input bias current, okay? So this large resistor is used to cancel this out, okay? The problem is that if you were to do this, what happened is that the input bias current also depends on temperature. So, maybe you start off at 50 picoamp, and then as you run the op amp hotter and hotter, it goes up to 200 picoamp, right? So unless you can have this circuit, right, at a fixed temperature, right, this is going to be a problem anyway. So, and what ends up happening is that you may even overcorrect for the problem or undercorrect it. And this is going to be not the best way to solve it, okay? This other circuit, right, is just another way with just 2 resistors instead of 3. So I will actually use the second way. But they basically does the same thing. Provide a little bit of input bias current so you can offset that from the chip, okay? So let me show you why, this picoamp of current, well, 50 picoamp or 200 picoamp current can cause a problem, okay? So let's look at this circuit where we just have a unity gain amplifier, and we wanted to get rid of some DC offset. So therefore, right, we'll put a little capacitor here just to, in case there's some DC offset that we can get rid of. We don't want DC current to flow into the positive, the positive input of our op amp, right? But basically you're just decoupling it, okay, with a capacitor. Well, you would think, oh, that's a good idea. But what happens that, right, the input bias current, okay, is going to be drawing current from both this, inside, right, bias minus IB plus, right? It's going to be drawing current from here to ground, okay? As it starts to draw current, right, your positive charge is leaving here, so you start developing a negative charge here. Well, whatever happens on one side of the capacitor, the opposite charge will develop on the other side. And now you basically have a positive delta V across this capacitor, right? You just made a little voltage source here, right? Okay, and this builds up over time because, right, this input bias current is so small, right, but it's happening all the time, okay? So as this current builds up, as these charges built up, right, you're going to start getting basically an input that's shifted up by, actually it's V Q over C, right, whatever the charge is, okay? Okay. You see this when people in electronics start studying these things called baseline shift. Basically, your input, is supposed to be centered around 0, but then as time goes on, it starts shifting up and up and up and up and up and up. And then that's going to cause a problem because you were expecting your input to be, between +1 and -1 volt. But then, if you run the thing for, 5 minutes, now it's between 2 and 1 volt. Sorry, 2 and 1 volt instead. Well, sorry, 2 and 0 volt instead, because you have this baseline shift. Okay. The way you fix that is by basically allowing that current to go to ground, because as this current runs out, right, it starts building charges here. And you just have a little resistor to ground that allows these electrons to escape to ground, okay? And that will be a little bit better in this case, okay? And we're going to see how these circuits are going to be useful in instrumentational amplifier, because we actually need these unity gain amplifier for us to make sure that our input impedance is high enough, okay? The other thing we have to worry about, over 30 minutes already, okay, is the input offset voltage, okay? If you go back to the data sheet, you're going to find that the input offset voltage for the LF411 is actually typical, is 0.8 millivolt, maximum 2 millivolt, okay? And this is actually caused by slight difference in the manufacturing of the transistor. So even though they try to match the transistor to be in pairs, they may not, the two, even though you make them the same way, maybe just an extra layer of atom on top of the P semiconductor, then you're going to have a slightly different beta between them. Okay. And you have to do the same thing with the resistor value. Remember, there's a bunch of resistors and capacitor and a diode inside your op amp. Okay. This means, right, your V out is not actually exactly what V in plus minus V in minus, right, times A, right? It's actually that times about plus or minus 2 millivolt. Okay, so this is you're gonna find that this 2 millivolt, right, it's going to be drifting around your input. You can actually trim this once again with a low voltage divider trick, where you find that your V in plus is always just slightly higher, right? Then what you do is you do a low voltage divider to subtract that out. But once again, this is often a temperature dependent offset. And so oftentimes you actually just want to look in the specification and you want to find an op amp that is, at least 2 to 3 times better than what your application demands. So in this case, right, I would not trust using, the LF411 to amplify anything that's less than 5 millivolt, for example. Probably 6, just to be safe. Right? Okay. So that's another aspect of operation amplifier that we have to worry about. So, and the thing is, the price of these amplifier does not go linearly with the decrease of these tolerance. If you want an amplifier that's maybe twice as good, right, a 1 millivolt offset is going to be 4 times as much. If you want one that's 10 times better, it's going to be 100 times more. So the tighter the spec, the more expensive these things get. Okay. I'm going to start this next subsection next lecture, because I'm already almost at 40 minutes. So I will upload this and see you on the next one.